Thank you very much, John, for the very nice introduction, and thanks again for inviting us here. It's really a pleasure to be here and talk about the methods that we are talking about. So indeed, the adaptive order, high order methods on our side has started with FEMAO, finite element method, and my colleague Adrian indeed initiated those. And today we will talk about the BEM. And then I will aim for half an hour on my part, where I'll talk about the theory and some industrial applications. And then I will leave the floor to you, who will take the next 15 minutes to also talk about a fast frequency algorithm that we applied to these boundary element methods. Right, so this is a bit the outline on my part again. So I'll try to talk a bit about like from the design process of BEMAO, like looking at the current challenges of BEM, how we kind of design BEMAO around that. I'll show some numerical validations, and then I will also try to show some more realistic industrial applications in this, and I will conclude and pass the word to you. So when we talk about current challenges of BEM, so we have identified three at the time when we were thinking about like our next BEM solver. So of course, the very first one is, as ever, the high computational cost for large models. That's not going away anytime soon. So we always try for faster methods. But there's also the second challenge, which is, of course, yeah, wave phenomena as it is that frequency dependency makes that you have actually different wavelengths. If you, so you have two ways to tackle it, right? If you want to really be performant, you would ideally provide multiple discretization of the problem over the frequency. Of course, now I'm still even talking about like in the deterministic ranges. I'm not going to kind of an SCA kind of thing, but really, mid frequency to low. But even there, you see wavelengths really changing quite a bit. And then, so this is so you either say like, I will try to do like multiple discretization, but that's a challenge. Or you'll say like, okay, I'm actually gonna, give a finest discretization at the highest frequency that's valid, and then I will just keep using it because I don't want to spend hands-on time. So this is a bit the current challenge as well. And of course, the third one is to also that we need these classical, if you think about classical finite element bounded element methods, they rely on also homogeneous discretization of the geometry. And of course, today the measures like the industrial are quite advanced, but it's still they're never perfect, right? So, and then, okay, how are they addressed today? Of course, the high computational cost, we look at like more scalable methods on fast multiple BEM and H matrix type of simulations. And again, like if you look at the second challenge, typically in industry, then it's just like a single mesh being used to really for the full frequency range, jeopardizing a bit the computational cost, but saving valuable hands-on time. And in terms of the non-homogeneous outcome of the measures, I mean, they are not extreme, let's say, but typically you would say then yeah, you either over discretize if you want all of your elements to kind of follow the 6 elements per wavelength criteria for linear elements, or you just say, okay, some of them are violating, but you accept a bit of loss of accuracy. So this is, as we see it today, the current situation with BEM. So when we were thinking about then our next BEM solver, these were a bit like the three blocks that we wanted to address. Of course, we want accuracy, the first of all. We want performance, but we also, very importantly, want ease of use. So we want our simulation models, we want our simulation technologies, tools to be accessible and used by not only experts, but also non-experts, that they don't need to do a PhD on BEM to be able to use these methods, but a bit of hand-holding at least to what we call democratization of our simulation tools, really trying to push them to to make an easy entry. Okay, so the first thing when we are talking about BEM, there are various formulations of BEM in literature. In specific to BEMAO, we have opted for what we call indirect variational BEM formulation. It's a symmetric Galerkin formulation. So going back to the indirect variation formulation, indeed, like there's a hypersingular operator there. We kind of address it by using Stokes theorem, so it becomes weakly singular. Again, this is quite well known, this formulation in the BEM community.
Now, the second part of it is the more interesting part, the high-order shape functions, because again, now we're following the footsteps of BEMAO. And the whole philosophy around this is I would like to kind of make an analogy to model DOFs versus nodal DOFs. I mean, what we are trying to do with high-order shape functions is we basically try to carry more info per degree of freedom. So what this will allow us to do eventually is actually compress the system size. So instead of using linear fine elements, we will try to use as large as elements are possible by using high-order shape functions, and that will allow us to compress our system. Instead of using 100K DOF, we will try to do it maybe like a 30K DOF, something like that, around that. So this is our choice of shape functions. We are using Lobato shape functions. They are also known as integrated Legendre. And for our implementation, so far, we are supporting from order 1 to order 6. So I will also show a bit like this compression capability, how far we can compress actually using these high-order shape functions. But there's, of course, a bottleneck first if you want to do a classical isoparametric approach, because our geometrical discretizations are driven by state-of-the-use meshes. So what we are then going for is the non-isoparametric approach, which is also known as basically P-band. So we are really kind of disconnecting the geometry discretization and field interpolation. And for our field interpolation, we will try to use our high-order shape functions. For our geometry discretization, we will conform to the state-of-the-use measures, and preferably to be combined, because we want as large as elements as possible, preferably second-order Lagrangian curved meshes. Okay, about quadrature, because this is typically one of the critical points of BEM. Because we want to use high orders, analytical methods were not possible to use. There are also other techniques on singularity subtraction cancellation, but our feeling was that it modifies the kernel a bit too much. And from an industrial point of view, where we want to actually support all the combinations of different boundary conditions, that was not as nice. So we resort to these very nice singularity canceling quadrature rules driven by Sauter and Schwab. So these quadrature rules, then when you have them as a library, quadrature library, they can be applied to all kinds of elements there. So and we use like a 3A3, 3A6, quad 4, quad 8 type of surface elements. So all of them and all their combinations. So and of course, yeah, they're brilliant mathematicians who really did the heavy lifting on that. What basically this quadrature rule does is that they subdivide this double surface integral that we need to solve for the coinciding elements in this IBAN formulation, and so they do this in a way that every subintegral has a Jacobian that cancels actually the singularities of our kernel. So which is brilliant, and then it's really then a clean way of tackling these singularities. Plus, again, it allows us to nicely use these high-order shape functions and integrate them. All right, but I'm talking about the performance of high orders and compressibility, so I'll try to now demonstrate that. So let's try with a bit of a simple problem. We have 1 cubic meter cube. We will have two configurations: a velocity excitation on the side. It's a bit more smooth problem, of course, but to make it a bit more exciting, we will also just put a point source excitation, which would create a bit of a more harmonic or more complicated field for us to look. So, and again, so there's no adaptivity yet. So we're just looking at like taking a given mesh, assigning order 1, order 5, or this kind of field order, and then just doing H refinement with high orders, right? So with the again, what we wanted to see a bit like convergence characteristics of these high orders. So and so we are looking at 1 kilohertz. Like I also like to use this Ka concept, so K being the wave number, A being the characteristic length of the problem. So this would be like Ka 30, around 30, that kind of problem. And you will see here the number of degrees of freedom versus relative error, and you will see going high orders for like 1% error for how much actually it compresses in terms of degrees of freedom, but also like the nicer convergence qualities. And then if I look at now the unit velocity excitation, again, you see a bit similar very nice convergence characteristics, and really compressing the model. So to be exact here, so at 1% error, a 60K DOF order 1 problem, we were able to represent it with around 5K DOF order 5 problem. So this is a compression of 12 times. And if I look at the computational time, the full computational time, including assembly and solving, it would be like this problem in particular took 85 minutes to calculate it order 1, while it took 1 minute to calculate it order 5. So again, there's no adaptivity here. We're just showing why we want to go high orders. And you can see here that how powerful they are actually, how much they can compress the problem, and how you start to see a bit this acceleration due to that compression. All right, but it's not the full story. Of course, that was a bit of an academic one. And on one hand, we want to compress the system, but when we talk about especially large problems, and if you think about assembly acceleration, assembly is still costly, because even if you introduce these higher shape functions, the quadrature points should still be dense enough to capture the wave field. So the operations on the quadrature still it's not changing. You're saving on the system size. So if you know our legacy software coming from from 90s, SysNoise, and then it became Virtual Lab Acoustics, and today it's SimCenter 3D Acoustics. So if you know this IBEM formulation there, what was being used there, what's typically used there, is that it exploits reduced quadrature. So as you go further in the field, and the typical setting was, I guess, like 5 elements after 5 elements later, instead of using 4 Gauss points for a triangle, you would use a single point for a triangle. Now, of course, then this has worked quite well over the years. Of course, there were some scenarios where you had to kind of increase the quadrature, and it's an approximation. But of course, because it's in the far field, it was working. Now, but it becomes much more difficult, of course, when you start to have higher order shape functions, and if you try to do this reduced quadrature kind of mentality, because you would have a combination of order 5 element here, order 3 element here, and like how much you're gonna go forward, it really becomes very complicated. So, but of course there are like these nice technologies, one of them being multi-level fast multiple algorithms that substantially accelerates assembly. And the scaling of the assembly algorithm would be typically n square, and with multi-level fast multiple algorithms, it would go to n log square n. And not only that, it actually accelerates, but it actually allows us to control the error robustly, much more robustly in the far field. So this is what we use for accelerating the assembly. There was also, we are, of course, we have a bit of our own flavor there as well. We are not using classical octrees because of our also like different kind of requirements. But so you can find more info about in this ISMA paper, where we talk a bit about our take on fast multiple implementation. But this is from a philosophical point of view, how we accelerate the assembly. All right, now we come to system solve. So you compress the system, we accelerated the assembly with fast multiple, and then we are at the system solve. Now, the difference, of course, like when we talk about, if I say fast multiple, FMBEM kind of, the first thing that people think about are iterative solvers, rightfully. But here, in our released version at the moment, we are going for direct solvers first. Why? Because we managed to actually compress our system. So what used to be maybe an industrial problems 150K linear model now is reducing to 50K. If it's a 50K model, it's reducing to 20K. But this compression actually allows us, like it puts us in a region where dense solvers are still efficient. So of course they're not scalable. It would be like still cubic n scaling, but they're efficient. And it also allows us to exploit like other hardware, like we also can exploit GPUs and so on, for instance. In the release version, this GPU is not yet supported, but it's in the roadmap, it's coming up. And then, of course, here there's a study we did some years ago just to compare. Of course, when you're comparing CPU, GPU, it's never fair. I mean, how many CPUs you can use, but this was a scenario in cloud, just what was available there at the time, a CPU-based versus GPU-based, and What we did with the GPU solver is that there's an external library called Magma. So we took it, we modified it to be able to do our Bloch-Kolaski solve. And it also allows multiple GPUs. So you're not restricted to the GPU of the memory of the GPU. So it's distributed. So it also allows then much better scaling if you want to go 3, 4 GPUs and so on. So it's a bit of a brute force approach, of course, you thinking that it's dense metrics. But anyway, but it's the reality. When you go to the servers and so on, these are the hardwares that are available, and we can actually exploit them. But of course, then it also means that the positioning of BEMAO, how we see it today in the release version, is for small to large problems and not for ultra large problems. So if you want to go, so let me maybe clarify what I think is an ultra large and what is small to large. A passenger car up to a couple of kilohertz, again, like Ka value around 200, that's what we call, that's what we call a large model. And then an ultra large model would be trying to push that car to 5 kilohertz, 10 kilohertz, and that would be ultra large. But of course, then you need really a method that scales, and that would be like an iterative solver. And then I can confirm that this is on the roadmap. This is something that we are actively working. You especially is the person who's taking the lead there. Okay, now the interesting stuff as well is the automatic adaptivity. How do we do adaptivity? Well, first of all, in terms of error estimators, as it is with our FMAO solver, we are using a priori error estimator. I know in literature and in our academic communities, posteriori error estimators are being used. It is of course much more robust if you go that way. But for our industrial needs, we needed a one-shot approach. We cannot afford typically doing loops and launching things and checking it again. So we are going a priori error estimator. Again, at the time, as Adrian talked, it is heuristics. It is not a conservative error, but the problems that we are seeing, both from FMAO side and BEMAO side, which I will also show a bit later on, all indicates that we can actually be still quite accurate with these approaches, and we just see that it actually works. Of course, you will, depending on the problem, you may end up at you can target, let's say 1% error, and in some problems you may end up like 3% or 5%, or even maybe like the other way. Of course, that shift is expected. But I can confirm, what I can confirm is, like, again, on all the cases that we are looking at, it doesn't break down. So we are not seeing it is breaking down, and we feel that this is for industrial cases, this kind of a one-shot approach is much more efficient and it's working for us. So we are doing assigning orders for each edge. So it's edge-based algorithm and per frequency. So we have these pre-calculated rules based where we looked at representative problems and came up with these rules. And we have defined like 3 predefined accuracy levels, coarse, standard, fine, for our users to choose depending on their accuracy requirement where they would like end up. Now the adaptivity there are two adaptivity, let's say, concepts here. So adaptivity for single frequency, adaptivity for frequency. So for single frequency, this would mean that you can actually feed a non-homogeneous mesh, like you can see here, and the solver will assign automatically orders. So for the larger elements, it will assign high order shape functions. For the smaller elements, it will assign lower order shape functions. That would be like this adaptivity for single frequency. But as you go through the frequency sweep, as you go to higher or lower frequency, the solver will also assign, because of per frequency, per edge algorithm, that will find the most optimal size of the model for that frequency. All right, so let's look at a numerical validation. We start with a plane wave scattering from a rigid sphere. It's 0.5 meter diameter. We have 21 microphones. That's in the shadow region. There's a plane wave coming from here. So this is how we would like to have a BEMAO mesh, coarse, curved, as coarse as possible. And this is a typical IBAM mesh, classical BEM mesh that you would have for the frequency range that we are targeting, a very refined mesh. And here it's like 17K nodes. Okay, if I now look at the accuracies, so you see 6 BEM figures, that would be like coarse, standard, fine, and coarse, standard, fine with assembly acceleration. This is to just also show, okay, the assembly acceleration, it's a fast multiple algorithm, there's an approximation, but it's quite controllable, so you can actually really be spot on with the non-AA version. And the AA version is our standard by default on. And here, if you look at the BEM, fixed order 1, you will see, of course, the error is increasing by frequency as expected. But if you look at the BEMAO ones, that this is the error that we are trying to control, and you see a much more smoother curve that targets 1% or standard, like 5% on coarse, and 10 to minus 3, so 0.1% in the fine accuracy. So here, for this problem, the KA range was from 23 to 37. Okay, let's look at some order distributions. Because for each frequency, the solver will assign a different order distribution. So with the coarse, you can see like at the lowest and highest frequency, and that we are representing here like 6 orders, and this is like the percentage of orders in total edge length. That's how we are reporting the statistics. So here the coarse model would have like majorly 2 1/3 order. At the highest frequency, you can see as you go to the fine accuracy, you would increase the order distributions, and here are the total number of DOFs. Again, you can see for a frequency sweep how much it changes. If I look at computational time, so this is like an 18K linear BEM model, you would require, so it's like 300 frequencies, 5 first step between here, and it would take us 18 hours to use a classical BEM approach. And if I use a coarse BEM, again, like between min and max, the simulation times changes. And if you look at the total, you see how fast we start to be as compared to classical BEM. And here it would fall in between coarse and standard accuracy with BEM. And you can see here from 1,000 minutes to like around 10 minutes if you want to see a bit of an accurate. So quite a bit of speed up. All right, a bit of a bonus round. So once you solve, when you're post-processing, you write the Kirchhoff-Helmholtz integral equation. If your field point is very close to your surface, it's actually what they call this near field singularity problem. It's very nasty. It's been there forever. And here the specific problems, because now you're also having large elements, this becomes even more pronounced. But we also have a solution for that. So typically, if you just take it just classical Helmholtz integral equation, integrate, your field points would have these hot spots when it's kind of going through. We also have a solution for this. We haven't published on that. It's been some time that I'm planning it, but it's been slipping. I'd like to talk about it in a later stage. But that just as a like teaser, let's say that there's also a treatment for near field singularities in our solvers where we can handle these kind of singularities. All right, so BEMAO as a solver, again, we aim for accuracy, and for that we use singularity canceling quadrature rules. We aim for performance. We are compressing the system size using high-order shape functions. We are using fast multiple method to accelerate our assembly, and we are aiming for optimal performance per frequency. And we say ease of use because there's a priori error estimator depending on the user's requirements that they can choose the target level. We use automatic p-order adaptivity, and we use automatic quadrature rules. So even if you have a dirty mesh, let's say that this method can actually give you accurate results, the quadrature rules and everything are automatic. So for it's hopefully a ease of use for the users. All right, so let me, looking at time, I need to accelerate and still leave some time for you. I will quickly go to, because these are more like academic examples. I will show some industrial applications now. And okay, I should give credit to our product manager Karim Hamish, who did actually these simulations using our software. So here we are looking at a business jet application. So it's we have microphones at the sides, 100 meter. The jet is 100 meter above the ground. A classical discretization here would have like 20,000 nodes, and we have our BEMAO discretization smaller nodes. But of course, this is not the degrees of freedom. This is the nodes, and our system TOFs would be different. You can see here the results up to 500 hertz. We are now comparing with H-matrix Dam. And as a it's also one of the good acceleration methods. And so here we are solving 481 frequencies, and you can see that standard Dam will take so many seconds and so on. And H-matrix would be quite fast as well, but H-matrix does have adaptivity in its algorithms, but it's not as strongly adaptive as how our BEMAO would behave. And you can see here also as compared to H-matrix, the acceleration that we have from 28,000 to 5,000 seconds. So again, we are looking at uncoupled acoustic application. This is a submarine application. It's 62-meter long, and this is what they call submarine target echo strength calculation. Here, the 30K nodes, BEM, classical BEM, H-matrix discretization versus this kind of BEMAO discretization. We have 260 subcases for this case, and again, a linear standard BEM take so much time. H-matrix, of course, accelerating it quite well, but yeah, BEMAO in this case can even push it further. Car pass-by noise. So again, a classical discretization of 32,000 nodes. This would be our with curved elements and as large elements as possible, our BEMAO discretization. Here you see the results again, matching very well between H-matrix and BEMAO. 250 frequencies, 5 subcases, and you see between 22,000 from that to 2,000 seconds, still a substantial improvement of BEMAO. A Viber acoustic example. So here we are looking at a loudspeaker. It's a V coupling. So we have strong coupling and V coupling scenarios here. So the H-matrix solver we had only supports V coupling, so that's also where we compare. But we can also do strong coupling with BEMAO with our structural solver. So this is also how you see it's very important to include strong coupling in some cases. And here is the discretization of the H-matrix and IBAM. This would be kind of a discretization that we want to use for BEMAO. Again, if you look at the results, standard BEM takes too much. H-matrix in this coupled scenario is also taking quite a bit of time, 122,000 seconds, while BEMAO would take 1,000 seconds to do this frequency sweep. Final example, so 2 loudspeakers on a desk. You would, again, this would be like a 74,000 nodes with H-matrix, and this would be like 20,000 nodes is enough to represent it with BEMAO. Here there was actually a bug in the H-matrix solver that it kind of go above here, which is being looked at, but I think it was because of the very, very close meshes. But for the BEMAO modeling, that was the problem. But besides that, if you look at also equivalent computational times, you see also quite substantial improvement of performance with BEMAO. And again, if you started to go, okay, this was the last one I guess. So I mean, here is the region where the linear models we put for in these benchmarks. If you start to go like 250K DOFs, 500K DOFs kind of things, I mean, it's of course then you still need scalable like H-matrix can still scale better for those regions, or you need to go to FMBEM. But for the regions again where I mentioned like small to large models as we put it, we are seeing BEMAO, this adaptivity, compression with high orders are really paying off and accelerating it quite substantially, the simulations. All right, conclusions on my side. So we have shown now applications to also industrial applications, really improved benefits of this high order mentality coupled with an a priori error estimator. It's accurate, more efficient for a wide range of applications. I mean, from our point of view, it's been shown to be quite superior to and significant speed up to classical non-adaptive methods. And again, our next step would be to also introduce iterative solvers and also keep that scalability going at higher frequencies. All right.
Great. Thank you very much on a really impressive speed up some results there. Very nice.
No worries, Onur. Thank you. Okay, I'll try to explain, take over from here and try to explain our recent work on matrix-free fast frequency sweep based on loaner framework for boundary element methods. Yep. So the outline for the presentation is pretty straightforward. I'll start a bit of introduction and background and literature review of these type of applications. And then I will introduce the matrix-free fast frequency sweep method that we implement and incorporate in our BEM solvers, followed by some numerical studies and finally the conclusion. So talking about fast frequency sweep analysis, this is a typical requirement from industry in practice, because often when you analyze the system, you want to know the system behavior over a wide frequency range. Typically, you need to assign a lot of frequencies, need to run a lot of simulations. On one hand, this is very expensive. On the other hand, it's difficult to define a proper frequency step for the simulation. And in the application of BEM, this is even more challenging because in BEM, we have a complex frequency dependency in BEM matrix or system. So it's hard to determine whether it's a linear or quadratic behavior on the frequency dependency. And also in BEM, we have virus boundary conditions, which adds additional challenge considering pressure, velocity, and impedance boundary conditions, all these combinations together with open boundary conditions, junctions, and so on. All these combinations add a lot of complexities in the fast frequency sweep because we want to provide a unified or general solution to the industry that can solve hopefully most of the problems where they face. And last but not least, we hope that the fast frequency sweep method can cope with the existing fast BEM techniques such as H-matrix and fast multiple method, as Onur mentioned in his presentation. And this is also very challenging because for H-matrix and fast multiple methods, they need they basically accelerate the kernel. They expand the kernels and do some compressions here and there, and this propagates through all the integrals in the BEM formulation, and thus making it difficult to add an additional layer of a fast frequency sweep algorithm on top of it. So what have been done in the literature? There are some efforts indeed. Some straightforward methods such as interpolation among frequencies means. Basically, you select a constant frequency resolution over the whole frequency range and then do some interpolations based on the results. But the typical challenge here is that for phase interpolation is often difficult to have a nice interpolation. And a larger group of technologies has been developed or underdeveloped is based on the expansions of the BEM kernels for frequency decoupling. As I mentioned, this is particularly challenging technique if we consider to couple with H-matrix and fast multiple BEM. Some other techniques such as recycling strategies from the iterative solver, iterative solution. This is particular for FMBEM, but often this is limited to a small deviation among the frequency solutions. So instead of using these technologies, we tried ourselves to implement this matrix-free fast frequency sweep technique. This is not new. It has been applied to structures, to complex materials, and so on. But it is indeed the first time that people implement, or we implement this in the different BEM solvers. So I'll briefly go through the theory here. So if we consider a second order system in general, and we have a complex matrix and complex stiffness matrix, complex mass matrix and stiffness matrix, sorry about that, then we can write the transfer function for this steady state system into this formulation. And the matrix free is basically relying on a two-sided Krylov projection. So these would help us to end up with a reduced order model, which is H hat. And there the reduced order mass and stiffness matrix can be expressed by using loaner matrix and shifted loaner matrix. And in this way, we can see that the final formulation of these two matrices is indeed using the transfer functions itself instead of the system information from BEM. So basically, all these transfer functions at the selected frequency mu and lambda can be computed by using the BEM post-processing step. These selected frequencies are determined iteratively and adaptively based on our error estimators. And on the right, you can see an example of how this matrix-free approximate to the full model iteratively. On the top is the FRF curve, on the bottom is the error indicator. In the end, we have a very nice match compared to the full order model. Yes, so next I will show you some more examples using matrix-free together with H matrix and the fast multiple BEM, and also our new BEMAO solver. So the first example will be a open back loudspeaker. We have a open boundary condition at the back of the speaker, and after the meshing, we end up with roughly 40,000 elements and 20,000 nodes. The excitation is a velocity boundary condition on the diaphragm. In this case, we consider frequency dependent impedance, which is assigned inside the loudspeaker. The frequency curve, the impedance curve was generated by using a GCA model. And for the matrix-free setup, we use the same frequency range and frequency resolution as an input. And also the target accuracy in this case is set to be 1%. And in the full order model, we consider a wide frequency range from 2000 Hertz to 3000 Hertz with a resolution of 1 Hertz. So in the end, we end up with 1,000 frequency simulations. And on the in the figure on the right of in the figure, you can see a comparison of the matrix-free with the full order model for 3 different receivers in the setup. So basically, we can see that the matrix-free captures the behavior of the system very well. And the vertical dashed line indicates the frequencies that has been selected automatically by the matrix-free algorithm. So in the end, for the reduced order model, we end up with 38 frequency beams. And in the second figure, you can see the relative error between a matrix-free and the full order model. In general, we end up with very good accuracy below the target accuracy, which is 1%. There's an exceptional case at around this 2,750 Hertz. But if you look back at the original response, there's a small spike, but it's not significant. So we consider this is acceptable in the simulation. And the second case is the same speaker, but instead we are using a rigid boundary condition all over the geometry. This is more challenging because of the interior resonance in the volume. So in fact, we have a more oscillatory response, which is shown on the right. And in this case, we can observe that the matrix-free indeed deployed more frequency beams in the simulation of the full frequency range. So we end up with 98 frequency beams for this case. And it can also observe that matrix-free automatically deployed more frequency beams when there's a spike in the response. And if we check the relative error in this case, overall, it's matrix-free maintain very good accuracy. There's a little bit, there are several outliers, but it's due to the interior resonance. And again, we think this is quite acceptable. considering this rigid boundary case, a lot of spikes in the response. Yep, and the next case is a simulation with fast multiple BEM. And in this case, we consider a model airplane with rigid boundary condition. The excitation is the velocity, prescribed velocity on the turbine, on both sides of the turbine. We have 52,000 elements, and for the iterative solver, we consider 10 to minus 3 tolerance, which is widely used in engineering practice. And for matrix 3, we use 1% as before. And in this case, we consider a wide frequency range from 1 kilohertz to 5 kilohertz. In the end, for the full order model, if we take a 2 hertz resolution, we have nearly 2,000 simulations. And by running matrix 3, we can significantly reduce the simulation number to 46 in the end. So in the figure, we compare 6 receivers, which are under the airplane. And again, we see a very good match between matrix 3 and the full order model. And in fact, if we check the relative error, all the response are below the target. Yeah, the last example is on BEMAO. Here we consider the same sphere from Onur's presentation. And in the classical indirect BEM mesh, we end up with 36,000 elements. Using BEMAO, we can significantly reduce the element number to 500 roughly. Since BEMAO provides a optimized solution at different frequencies, the size of the BEMAO model also changes according to the frequency. In the end, we have a model size of 6,500 to 900 DOFs at low frequency. So in this case, we compared different setups using BEMAO and BEMAO with matrix 3. If we take 1,000 hertz to 4,000 hertz for this sphere case, with indirect BEM, we end up with roughly 600 simulations. That will be 41 running time. And with BEMAO standard, for the same full order model, we can reduce the time to 45 minutes. This is already a great reduction in time. But on top of that, if we consider a fast frequency sweep from matrix 3, we can further reduce the total wide frequency simulation cost by reducing the number of frequencies required in the simulation. And for fine and standard, we end up with 54 frequencies. And for coarse mesh, we have a bit higher number of frequencies. And this is also because of the accuracy in the coarse setup is a bit less than expected, than the standard. So if we take a look at the figure on top, we can see that for this red curve, which is the BEMAO standard, and we compare the yellow to the yellow curve, which is BEMAO standard with matrix 3, we see quite similar accuracy. And the reference in this case is analytical solution. And for BEMAO fine accuracy is even better, of course, and the course is a bit above than the standard, but still similar to the classical IBEM formulation. All right, so conclusions. So in this work, we consider a matrix 3 model order reduction technique to address the wide frequency, fast frequency sweep analysis in BEM solvers. And the matrix 3 algorithm is operating on the FRF level. That means it doesn't interfere the BEM kernels, which is nice for H matrix and fast multiple BEM. We also implement a smart or adaptive error estimator that can help the algorithm to determine the frequency adaptively and iteratively. So the user doesn't need to give information, provide extra information to the system, which is nice, especially when the user doesn't know the system behavior a priori. The algorithm can be coupled to different BEM solvers. As I showed in the presentation, we have classical IBEM, BEMAO, H-matrix, and FMBEM, and it's efficient by reducing the number of frequencies required for the wideband simulation. One thing I didn't mention in the presentation is the parallelization of the algorithm, which is possible by using divide and conquer strategy. And last but not least, the accuracy level that the matrix-free provided is very acceptable in our opinion. So in general, the matrix-free fast frequency sweep for BEM is promising for many applications, especially the system behavior is not known in advance. And also, especially for cases that a fine frequency resolution is needed, for example, for oralization cases or calculation of HRTF, for example. And these are cases where we believe the technology can shine and help to accelerate the simulation. And the work has been published in a recent GSV paper, which is shown at the bottom. That concludes my presentation. Thank you so much.